How big is the universe? It sounds like a simple question, but the answer is anything but. When we talk about the size of the universe, we're diving into distances so vast they break intuition, a history stretching billions of years, and a cosmic architecture that reshapes what we think big even means. From the smallest planet to the farthest galaxy, and beyond the horizon of what we can even observe, the scale keeps exploding. By the end of this journey, you won't just see how unimaginably vast the universe is, you'll understand why its size is one of the most profound mysteries science has ever faced. When we talk about big, especially with the universe, the first trap is thinking of it like a big room, an immense container, with walls somewhere on the outside. But that idea? It falls apart right away. The universe isn't inside something bigger. It is everything. Everywhere you could ever go, everything you could ever measure, and every dimension of reality itself, space, time, energy, are all part of the same continuous system. So there's no outside to measure. That right there, that kicks your instincts out the window. Because here's the thing you need to understand. Size isn't just about distance. We're not just talking in miles or kilometers from one end to another. The universe doesn't make it that easy. It's also about time, how long it's been growing. It's about limits, because there's only so much of it we can even observe. And here's the kicker. The true size of the universe might be infinite. Not just big, infinite. Think about that word for a second. No borders, no edges, no place where it stops. And if that makes you feel like everything in your brain just short-circuited, you're not alone. But here's another problem. The moment you start trying to imagine how big even our part of the universe is, the part we can observe, your brain just isn't built for it. Forget imagining galaxies. Most people can't even hold the size of Earth in their heads. And Earth? It's beyond microscopic from a cosmic point of view. The distances we're about to explore are so enormous that they rip apart everything your instincts would normally rely on. This isn't just big. It's so big that even our words, our comparisons, start to break down. Let's clear up one of the most common misconceptions before we take this journey. The universe isn't expanding into some kind of pre-existing void, the way a balloon expands into the air around it. Space itself is what's expanding. It's not stretching outward into something else. It's stretching itself. This is critical because people always imagine there must be an edge to reach or something waiting on the outside. But what's outside the universe? That question doesn't even make sense, because outside doesn't exist in this case. Space itself is the stage. Everywhere is the stage. Now, before we go any further, we need to make one massive distinction: the difference between the observable universe and the universe as a whole. What we call the observable universe is just the part of space that we can see, the part where light has had time to travel from since the universe began over the 13 billion years ago. But here's the mystery. Beyond that, there's more. Maybe a little more. Maybe infinitely more. We don't know. The observable universe is just the slice that makes it to us. What's out there beyond that? It could go on forever. It could circle back. It could be something that shatters everything we think we know. And here's the wild part. When you look farther into space, you're also looking farther into the past. That little twinkling star you point a telescope at. Its light could have taken thousands, millions, or even billions of years to reach us. By the time you're looking at those distant galaxies, you're not seeing them as they are now. You're seeing them as they were billions of years ago when their light first started travelling. That means asking how big is the universe is also asking how far back can we see? Distance isn't just distance, it's time travel. That adds a whole new layer of mind-bending complexity, because the picture you get of the universe is really millions of different snapshots from millions of different times. But let's take a step back for a minute. Before we get too lost in cosmic distances, let's return to where this all started, Earth. Because here's something crazy to think about. To you, Earth feels enormous. It takes over 19 hours to fly from New York to Singapore. We talk about our oceans as unimaginably vast. But Earth, compared to the universe, it's a speck. Not even that. And that's why we start here. because even making that leap from Earth to space is enough to shake your sense of scale. Earth has a diameter of about 12,742 kilometers, or roughly 7,918 miles. That's massive enough that if you stood on a hill, you'd only ever see a tiny, tiny fraction of this one rocky world. It feels huge, and yet it's almost nothing when you leave the ground. Let me illustrate how small Earth is. If our planet were the size of a basketball, the moon would be a tennis ball orbiting more than 7 meters, or about 24 feet away. And the sun, forget comparison, it would be over a kilometer off, or nearly 0.62 miles, and its size would dwarf anything in sight. Now hold on to this thought, because it only escalates. Even Earth's atmosphere, this shield of air that makes life possible, turns out to be just a fragile sliver. Most of the air you breathe is crammed into the first few kilometers, or just a few miles above the surface. Fly upwards just 10 kilometers, or about 6 miles, and you're already leaving the densest part of it. From space, Earth looks like a giant marble, but that blue glow you see fading into black? That's not some massive ocean of atmosphere, it's a paper-thin layer stretched around a rocky ball. And compared to the void of space, well, put simply, Earth's home bubble is next to nothing. But here's an even bigger realization. Earth feels eternal to us. It's always there, always connected to us. But in space, Earth is completely and utterly isolated. The closest major celestial body, the Moon, is over 384,400 kilometers, or about 239,000 miles from here. Long enough to fit every planet in the solar system lined up in that gap. It's hard to even visualize that distance, and yet that's as close as it gets. The gap to even the nearest planet, let alone a star, is so colossal that our connection from Earth to anything else feels almost insignificant. And guess what? That distance to the Moon is still just the first baby step on a much larger cosmic journey. Here's the lesson that's hard to swallow. We care about Earth because it's ours. Life exists here. We live here. But reality doesn't place any special importance on it. In the grand scale, Earth isn't large, central, or cosmically privileged. It's just one ordinary rock circling one ordinary star. But from this one small corner of existence, humans did something incredible. We started looking out, asking how big the universe is, and building the tools to find out. Now we're going to climb step by step, out to the Moon, then the Sun, then beyond, because the real journey outward is only just beginning. So let's start with somewhere familiar, Earth. To us, here on its surface, Earth feels enormous. We live our entire lives without really seeing it all, or even fully grasping it. Think about it. Our oceans are so vast that ships crossing them seem to disappear into the horizon. Our flight routes can span thousands of kilometers across oceans, continents, and mountains, taking hours or days at speeds that are mind-blowing on a human scale. And when you zoom in, life feels infinite in terms of sheer variety. Earth's climate zones range from frozen polar ice caps to scorching deserts to dense rainforests teeming with diversity. In every way that matters to daily life, Earth feels like an unimaginably massive place. But here's the twist. As soon as you step out of that human perspective, just a little, Earth's size starts to feel less impressive. Let me hit you with this mental shift. If you took the Earth and set it beside the rest of the universe, oh boy, it's not just small, it's tiny. And that contrast, the leap from our Earth-centered intuition to the sheer scale of what's out there, is the first breathtaking blow when you start asking how big the universe really is. To put things into perspective, Earth's diameter, the distance straight through it, pole to pole, is a bit over 12,742 kilometers, or 7,918 miles. Sure, that sounds large to us. Most of us will never even travel enough in our lifetime to cover a fraction of that distance. But here's where the comparison game starts to sting a little. Earth is not special. In fact, it's about average when it comes to rocky planets like ours. It's smaller than gas giants like Jupiter, smaller than icy worlds like Neptune, and absolutely dwarfed by the Sun. Here's a number to chew on. The Sun's diameter is roughly 109 times Earth's. 1 million Earths could fit inside the Sun. Now think about that. If you were standing on Earth looking up at the Sun, you'd only see a tiny circle in the sky. But in reality, the thing is so massive that our entire planet is just a speck in comparison. That's our first big hint. What seems big to us is nothing more than a drop in the cosmic bucket. And every time you think you've got a sense of scale, there's a bigger number waiting in line to knock you down again. But let's zoom in for a second and talk about something closer to home. Earth's atmosphere. To you, standing outside, the sky feels so big, vast enough to stretch endlessly above your head. Where does it even stop, right? Well, it turns out that beautiful blue blanket we call our atmosphere, the one shielding us from space, is no more than a wafer-thin layer compared to the full size of the Earth. Most of the breathable air, the part of the atmosphere that matters to you and me, exists within just 10 kilometers, or about 6 miles above the surface. Let me make that clear. If the Earth were the size of an apple, that life-sustaining atmosphere we rely on wouldn't even be as thick as the waxy skin. The sky might feel boundless to you, but in reality is barely a whisper on the grand scale. It's more fragile and fleeting than our instincts would have us believe. And that brings us to the next major shock. Earth feels like it's at the centre of everything because, well, we live here. It's the place where the story of humanity unfolded. It's our home base, surrounded by our mountains, rivers, and clouds. But here's the truth you need to hear. The Earth isn't central. It isn't even remotely special in the grand scheme of the cosmos. To put this isolation into context, think about the Moon, our nearest cosmic companion. The Moon is over 384,400 kilometers, or about 239,000 miles away. Close, right? Not really. At that distance, you could fit every single planet in the solar system side by side in the gap between Earth and the Moon. That's how much space even our nearness to the Moon contains. But beyond the Moon, forget it. Even the nearest planet, Venus, is so far away that the concept of closeness starts to lose meaning. Space isn't crowded. It's empty, silent. No matter where you look from Earth, the overwhelming majority of the universe around us is just vast black emptiness with a few scattered pinpoints of light. And that's just our local view. Imagine what happens when we go further. All of this brings us to one crucial understanding. Earth matters to us because it's home, but in the cosmic story, Earth isn't large, it isn't central, it isn't even all that unusual. It's one small ball of rock sitting in orbit around one unremarkable star in a remote corner of one galaxy out of countless billions. And before you let that make you feel insignificant, remember this. Out of that one small rock, we've managed to look outward. We've built telescopes, launched spacecraft, and asked questions that no other life form we know of can comprehend. How big is this thing we're living inside? The journey to answer that question starts here. From Earth to the Moon to the edges of the solar system, each step is going to make us feel smaller, and each scale will make the universe seem impossibly large. But trust me, we've barely scratched the surface. Let's talk about the Moon, the closest neighbour we've got in space. At first glance, the Moon feels reachable. It's right there in the night sky, big, bright and comforting. But here's where reality smacks human intuition in the face. The Moon is, on average, about 384,400 kilometers away from Earth, or roughly 239,000 miles. That distance is easy to say, but hard to grasp. To put it into perspective, you could fit every single planet in the solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus and Neptune, side by side, including their gaps for their diameters, in the space between Earth and the Moon. Go back and read that again. The distance to the Moon, something we feel is so nearby, can hold all the planets of our solar system just in that gap. So if you've ever thought the Moon was nearby, just remember how bad your instincts are at this kind of thing. This is just the start of how distance in space breaks down everything you trust about what feels close. And yet, the Earth-Moon gap? Astronomically speaking, it's nothing. That's because the Moon may be our nearest cosmic companion, But the next defining feature of our solar system, the Sun, is orders of magnitude farther away and larger in ways that will completely dwarf Earth and its little moon. The Sun is not just the centre of our solar system, it is the solar system. By size, by mass, and by sheer gravitational dominance, everything else in the solar system is basically just debris following it around. The Sun is about 1.39 million kilometres in diameter, or 864,000 miles across. That's over 100 times the width of Earth. More incredibly, the Sun's volume is so vast that you could fit more than 1 million Earths inside it. Put another way, if Earth were the size of a marble, the Sun would be a beach ball dwarfing anything else in sight. But there's something even crazier. The Sun accounts for 99.86% of all the mass in the solar system. Everything else, Earth, the Moon, all the planets, the asteroids, comets, everything is barely even a rounding error compared to the Sun. This changes the picture of the solar system completely. It stops being a collection of equally interesting members, the Sun, Earth, Mars, Pluto, and instead becomes one massive object surrounded by little leftovers. Remember how big Earth seemed just minutes ago? Well, against the scale of the Sun, it's barely more significant than the dust on your bookshelf. Now let's talk about how far we are from this enormous cosmic oven. The Sun is about 150 million kilometres, or 93 million miles, away from Earth. That number is so big that kilometres or miles start to lose their usefulness. Let me give it to you another way. It takes light, which travels at a blistering 299,792 kilometres per second, about 8 minutes and 20 seconds to cross that distance. That's the speed limit of the universe. Nothing can move faster than light. And it still takes over 8 minutes for sunlight to reach us. Here's why that's mind-blowing. When you feel the warmth of the sun on your skin, you're not feeling the sun as it is now. You're feeling sunlight that's already over 8 minutes old. If the sun for some reason disappeared at this very instant, you wouldn't even know for 8 whole minutes. Light doesn't travel instantly, and this will become a massive theme as we go on. You're never seeing the universe as it is right now. You're always seeing it on a delay. But let's stick with the sun for a minute to emphasize just how huge space really is. If the Earth's sun distance is called 1 astronomical unit, which scientists use as a shorthand to deal with solar system distances, then the next closest planet, depending on orbits, is anywhere between 0.3 to 2 astronomical units away. Venus and Mars might sound like neighbours, but the distances are still enormous. And even within the so-called inner solar system of Mercury, Venus, Earth and Mars, do you know what dominates everything? Not planets, not asteroids, pure, empty space. Here's something textbooks sometimes miss. Solar system diagrams make everything look cozy. Planets are drawn in neat orbits, usually clustered close together so they fit on the page. But in reality, the inner solar system is mostly nothing. The distances are so vast compared to the planets themselves that the idea of closeness stops making sense. Imagine Earth as a grain of sand. Venus would be another grain of sand a few meters or yards away, and the rest is empty desert stretching in all directions. This emptiness continues all the way out. The planets seem like this close-knit family clustered around the Sun, but the distances between them are so huge that the entire idea of solar system togetherness starts to feel like an illusion. And if the inner solar system is mostly void, just wait until we start moving outwards toward the gas giants and the edge of the solar system. It only gets emptier. The more we zoom out, the lonelier space becomes. Now, remember what I said about sunlight earlier? Well, the same goes for moonlight. Light from the moon takes about 1.3 seconds to reach Earth. Blink, and you've almost missed it. So when you're looking at the moon in the night sky, you're actually seeing it as it was 1.3 seconds ago. And that's nothing compared to the sun's 8-minute delay. That simple idea that light takes time to travel is about to completely change the way we understand distance. You'll see why as we keep scaling up, because once you move beyond the solar system, light travel time goes from seconds and minutes to years, thousands of years, even billions of years. At those scales, the universe stops being a place you can measure like a piece of land. It becomes a map through time itself. And that's when things really start to break our understanding of scale. When most people think about the solar system, they probably picture the planets: Mercury, Venus, Earth, Mars, the gas giants like Jupiter and Saturn, Neptune at the far end. Maybe they throw in Pluto for old time's sake. And sure, the planets are the stars of the show, the big, obvious objects that get all the attention. But here's a truth that's going to blow your mind. The planets are just the inner core of the solar system. There's a vast amount of stuff that lies far beyond Neptune, and these outer regions are so huge, so sparse and so alien compared to what we're used to, they don't even feel like they're part of the same system. But they are. So let me redefine the solar system for you. It's not just a flat set of 9-ish planets orbiting in neat circles. It's a gigantic, layered gravitational structure, like an onion with wildly oversized outer shells. Inside this system are not only the planets, but dwarf planets like Pluto, scattered icy bodies in a region called the Kuiper Belt, and, beyond everything you can imagine, a distant, ghostly sphere of frozen objects in a zone called the Oort cloud. The planets? They're just the bright, shiny centerpiece of a much more massive structure. And if you thought the solar system ended at Neptune, well, you're about to find out just how far off that assumption was. Let's zoom back in, though, for a moment. If Earth already seems big, then Jupiter, the king of the solar system, completely crushes our sense of scale. Jupiter is a true monster, so it's more than 11 times the width of Earth, at around 143,000 kilometers, or nearly 89,000 miles, across. If Earth were the size of a grape, Jupiter would be a basketball. But here's what really sets it apart. Jupiter is so massive that it contains more than 70% of all the planetary material in the entire solar system. Pause and think about that. Take every other planet, swirl them together, and Jupiter would still outweigh them. Does that make Earth feel small yet? Well, it gets worse. Jupiter is so enormous and powerful that its gravity has literally shaped the solar system. It flings asteroids around like billiard balls, protects Earth from some comet impacts, and even has its own mini solar system of moons, 79 currently known, some of which are massive enough to be planets if they weren't orbiting Jupiter. Jupiter is like the unofficial second-in-command of the Sun's gravitational empire. But even Jupiter, for all its sheer dominance, doesn't mark the edge of the solar system. No, the gas giant is just another signpost on the journey outward. Let's head out to Neptune, 30 astronomical units from the Sun. An astronomical unit, or AU, is the average distance between Earth and the Sun, about 150 million kilometers or 93 million miles. So Neptune is 30 times farther from the Sun than Earth is. That's nearly 4.5 billion kilometers, 2.8 billion miles. To put that in perspective, it would take light, travelling at 300,000 kilometers per second, about 4 hours to travel from the Sun to Neptune. And here's where it gets weirder. You might think, okay, Neptune is the farthest planet, so we're at the edge of the solar system now, right? Wrong. Neptune marks the end of the planets, but not the end of the solar system. Beyond it lies the Kuiper Belt, a donut-shaped ring of icy bodies, dwarf planets, and comets that stretches 20 times farther out. This is where forgotten outsiders like Pluto live, along with other icy objects that are so far from the Sun that sunlight there is a faint hint of what it is on Earth. The Kuiper Belt isn't an edge, it's more of a fuzzy transitional zone. The solar system doesn't just stop, it bleeds outward in layers, but even the Kuiper Belt isn't the final shell. Beyond it is something so vast and so hard to fully map that we can barely confirm it exists, the Oort cloud. Think of the Oort cloud as the solar system's distant icy frontier. It's not a flat ring like the Kuiper Belt, it's a spherical bubble of trillions of icy bodies, extending possibly up to 100,000 astronomical units from the Sun. That's 100,000 times the Earth-Sun distance. To put this in terrifyingly large terms, that could be as far as 15 trillion kilometers, or roughly 10 trillion miles. At that distance, the Sun is just another faint star in the sky, not the fiery, dominant presence we know it as here on Earth. It's a pale dot, barely bright enough to cast shadows. If the planets feel like the main stage, the Oort cloud feels like the ghostly outskirts of an empire that doesn't even realise it controls those far-off lands. The Oort cloud is thought to be the birthplace of long-period comets, like the ones that swing into the inner solar system once every 1,000 or even tens of thousands of years. It forms the true outer boundary of the Sun's gravitational influence. Nothing about the Oort cloud scale is comfortable. We don't even have spacecraft capable of getting there in any reasonable time. Even Voyager 1, the fastest and farthest human-made object launched in 1977, would take 300 years just to enter the Oort cloud and 30,000 years to pass through it completely, if it were headed in the right direction, which it isn't. But here's a crucial point. Exiting the solar system, even if you're lucky enough to cross the Oort cloud boundary, doesn't mean you're stepping into some bustling galactic highway filled with stars and planets. It means entering an even more incomprehensible emptiness, interstellar space. The nearest star system, Proxima Centauri, is over 4 light-years away. That's nearly 40 trillion kilometers, or 25 trillion miles, which means the gap between solar systems is essentially nothing. Stars are like tiny islands separated by vast oceans of pure void. The spaces between them make even the solar system's Oort cloud seem cozy. And so here's the cold, hard truth. The solar system, in all its massive complexity, is just a tiny bubble in the universe. It's a small, isolated island of things bound to the sun, and even then, most of it is just emptiness with the occasional icy rock floating in the void. The moment you leave the solar system, the scale of what we're exploring doesn't just increase. It explodes into distances so enormous, they make the entire idea of how big is the universe feel impossible all over again. All right. So by now we've left the immense shell of our solar system, crossed over its frozen outskirts, and approached what lies beyond, the stars themselves. The closest stars, these other suns scattered through the galaxy, hold a strange place in our intuition. We call them nearby stars, but the word nearby here is a cosmic joke. Let's start with the frontrunner, the star system closest to our own, Proxima Centauri. The shocking truth, it's more than 4 light-years away. That means the light from Proxima shining into our telescopes right now started its journey over 4 years ago. Stop there for a moment. Think about how fast light travels, 300,000 kilometers per second, and nothing in the universe can go faster. That's fast enough to circle Earth 7.5 times in a single second, and yet, at that breakneck speed, it still takes more than 4 entire years just to get to Proxima Centauri. It's the closest star to us, and already the scales we've been using to understand distance, kilometers, miles, even astronomical units, completely break down. That's the moment where distance itself changes meaning. If you left Earth right now on the fastest human-made spacecraft, Voyager 1, heading toward Proxima Centauri, which, spoiler it's not, it's going in a totally different direction, you'd reach it in about 75,000 years. 75,000 years. That's how far away the nearest neighbouring star is. And to be totally clear, Voyager 1 isn't slow either. It's ripping through interstellar space at 17 kilometers per second, or about 38,000 miles per hour. But the distance to just that one ordinary star is so staggering that our greatest machines suddenly seem laughably inadequate. So when we say Proxima Centauri is the closest star, what we really mean is it's just the least impossible to imagine. You might as well call the Moon nearby compared to Pluto. That's the kind of scale we're dealing with. And here's where we need to take a moment to clear up something crucial. Let's talk about the term light year, because it sounds like a unit of time, right? Something measured in years, but it's not. A light year is a unit of distance. It's how far light travels through space in one Earth year. To put it in raw numbers, in just 1 second, light travels 300,000 kilometers, or about 186,000 miles. Multiply that by the number of seconds in a year, around 31.5 million, and you get the distance light has traveled in that time, roughly 9.46 trillion kilometers. That's 1 light year, 9.46 trillion kilometers, or about 5.88 trillion miles. It's such a mind-bogglingly huge distance that for anything past our solar system, kilometres or miles are almost useless for comparison. That's why astronomers threw them out entirely and started measuring the universe in light years instead. Here's the catch though. Even this new cosmic ruler that's designed to be big, well, it starts to feel small disturbingly fast the moment we move beyond the closest handful of stars. Now let's pretend for a moment that you want actual interstellar travel. Maybe you want to hop in a spaceship and go visit Proxima Centauri. How long would it take? Well, like we said, something like Voyager 1, our fastest probe travelling at a blistering 17 kilometers per second would need over 75,000 years to get there. You're looking at more than 3,000 generations of humans just to complete one trip. Even if you magically increase the spacecraft's speed 100 times, adding advanced engines, beams from futuristic propulsion, or some wild new technology, you'd still need hundreds of years to make the journey. This problem isn't just about technology, it's about the sheer size of space itself. The gaps between stars are so massive that even radically advanced engineering starts to feel like a drop in the bucket. Now here's where things get humbling, maybe even a little unsettling. The Sun, the massive, overwhelming object that we spent an entire section proving dominates our solar system, is, on the cosmic scale, pretty ordinary. It's what's known as a G-type main sequence star. Not the smallest, not the largest, not the hottest or the longest living. It's just a middle-of-the-road star. And that's the trick. It feels massive and unique only because it's close to us. But if you zoom out to look at the Milky Way, our galaxy, which we'll dive into later, the Sun is just one star of hundreds of billions. Some stars in the Milky Way dwarf the Sun with tens or even hundreds of times its mass and brightness. Others, like red dwarfs, are fainter and smaller, burning for trillions of years. There are binary star systems where two stars orbit each other, trinary systems with 3 stars, and so on. The Sun looks big locally, but in the bigger picture of the universe, it's just another dot among countless others. Its grandeur doesn't extend far beyond its small corner of the galaxy. But here's an even deeper point about what we see when we look at stars. The space between them is a huge part of what makes the universe the size it is. Between the stars and a galaxy, the gaps are not just empty. Calling it a void doesn't quite do it justice because of how immense it really is. For instance, Proxima Centauri might be the closest star to us, but after that the next closest stars are all tens or hundreds of light years away. The distances aren't just large, they become almost meaningless compared to what we're used to. Sure, interstellar space contains some gas and dust, it's not a total vacuum, but it's so sparse it's hard to even fathom the numbers. For comparison, on Earth's surface 1 cubic centimetre might not hold billions of air molecules. In interstellar space, that same space might contain just a few atoms drifting across a mind-numbing gap. Most of the volume of the universe is, well, just nothing. Immense, sprawling amounts of uninterrupted nothingness. So here's a staggering thought to leave you with. Even after crossing the solar system, even after striking out into interstellar space, it feels like you're still nowhere. You've only ventured into the thinnest layer of your cosmic neighbourhood. All the stars we can see with the naked eye are like the houses on one street of an enormous city, and the gaps between them are so massive that it would take longer than the entire age of human civilization just to cross a single one. And this is where the scale of the universe starts to make you question how far we can even comprehend. If crossing the gap to the nearest stars already feels impossible, and if the Sun is just a single ordinary star in a Milky Way filled with hundreds of billions more, then what comes next? The answer? Galaxies. Brace yourself, because the jump we're about to take from stars to galaxies will make the vast emptiness between the stars feel quaint. Let's zoom out again. So far we've talked about the Sun, our neighbouring stars, the colossal distances between them, and the empty voids of interstellar space. But here's the thing. Those stars, all of them, belong to something much, much bigger. A giant, structured, spinning city of stars called the Milky Way. It's home, at least on a galactic scale, but get ready, because the staggering scale of this single galaxy is enough to break our concept of local entirely. The Milky Way is about 100,000 light years across. Let me say that again, 100,000 light years. At light speed, literally the maximum possible speed in the universe, it would take you 100,000 years to cross from one end of the galaxy to the other. Think about that for a second. Light, which can go from the Earth to the Moon in just over a second and travel around our entire planet 7.5 times in that same instant, would need 100,000 years to traverse the entire Milky Way. Even when we try to understand distances at this jaw-dropping scale, our everyday language starts to collapse under the weight of those numbers. To help orient this, every single star that you can see with the naked eye in the night sky is part of the Milky Way. But as vast as it appears then, what's visible to us is only the tiniest piece of the puzzle. The galaxy holds hundreds of billions of stars. That's right, billions. Many of those stars have their own systems of planets, billions or even trillions of worlds scattered throughout this one single galaxy. And let's not forget, while we see the Milky Way as a misty streak across the night sky, hence its name, this streak is just our edge-on view from deep in one of its spiral arms. If we could leave the galaxy and view it from outside, we'd see that it's a massive, nearly flat disk with long, curved spiral arms curling out from the centre. It would look something like a swirling pinwheel of stars. But here's the kicker. The Milky Way isn't just a random pile of stars thrown together into a vague shape. Galaxies are deeply organised. This one, for instance, isn't just a bunch of stars. The Milky Way has structure. It has a flat, thin disk where most of the stars, gas and planets sit, paraded into those spiral arms. Out toward the edges of the galaxy, you'll find less dense, older populations of stars, while near the core the density ramps up dramatically, with stars packed tightly together in the galactic bulge. Surrounding everything is a diffuse spherical halo of stars and dark matter. And yes, dark matter, an invisible form of matter that we'll get into later, is one of the reasons the galaxy can even hold itself together. Without it, the Milky Way's stars should have flown apart billions of years ago. Now, let's talk about where we are in this giant stellar city. If the Milky Way were an urban sprawl, you might expect our sun to sit somewhere near the bustling downtown centre. Right? It's what you'd instinctively think. But nope, just as our solar system is nowhere near the centre of the universe, it's also far from the centre of the Milky Way. The sun is way out in the galactic suburbs, specifically about 27,000 light-years from the centre, tucked away in one of the quieter spiral arms known as the Orion Arm, or the Orion Spur. It turns out the Milky Way, our home galaxy, is central to us only because it's ours. On the larger scale, the Sun is just one of billions of equally ordinary stars sitting far from the action. It's a fact that keeps hitting us, doesn't it? Each time we zoom out, we're reminded that our place in larger cosmic structures is not particularly special. But let's head to the centre now, because things there are truly fascinating. At the very core of the Milky Way lies one of the most awe-inspiring and terrifying objects the universe can produce, a supermassive black hole called Sagittarius A. This black hole has a mass estimated at about 4 million times the mass of the Sun, and while it might sound like an apocalyptic monster, it's actually not the galactic vacuum cleaner you'd expect from all those sci-fi movies. Even though this black hole is unimaginably dense and compact, it's surrounded by so much space, and the galaxy is so massive that most stars, including the Sun, are in no danger of being sucked in. In fact, the Sun's stable orbit around the centre of the galaxy is possible because of the galaxy's size and structure, not because we're on the precipice of being devoured by Sagittarius A. Still, it's kind of unnerving to think that at the very heart of our galactic home is an object where space and time themselves bend into something we can hardly comprehend. But here's a thought to blow your mind. A single galaxy is already staggering in scope. Hundreds of billions of stars, distances spanning tens of thousands of light years, gas clouds so enormous they could fit multiple solar systems inside them, star clusters, supernova remnants, collapsed stellar corpses like neutron stars and black holes. And with that, we haven't even started talking about how many other galaxies there are. The Milky Way is massive, but it is not unique, and it is far from alone. This is the first time we really understand that the Milky Way is not the universe. It's not even close. It's just one galaxy in a much vaster population. Everything we've covered so far, the sun, the planets, the nearest stars, the void between them, and the galaxy housing all of this, is just one relatively ordinary example of what the universe contains on a much grander level. And the moment we step outside the Milky Way, into the far reaches of intergalactic space, things are about to escalate in a way that will make even this enormous stellar city seem like just another speck. Alright, let's take this a step further. We've spent plenty of time zooming out to appreciate the sheer size and structure of the Milky Way, this massive city of hundreds of billions of stars spread across 100,000 light years. But here's the twist that will really mess with your head. The Milky Way, this galaxy that completely dwarfs our ability to imagine size in any meaningful way, is not alone. It's just one galaxy, one gigantic object among a staggering number of others. In fact, the closest major galaxy to the Milky Way is close enough to make all those unimaginable distances seem small. It's called the Andromeda Galaxy, and what it shows us is simple. The Milky Way is not special. It has neighbours. Andromeda is huge. Like the Milky Way, it's a spiral galaxy with a central bulge, sprawling star-packed arms, and a halo of dark matter. It's roughly 220,000 light-years across, more than twice the width of the Milky Way, and its size is only part of what makes it important. Andromeda is the nearest major galaxy, but here's what nearest means in this context. It's about 2.5 million light-years away. Let me hit you with that again. A light-year, as remember, is almost 9.5 trillion kilometres, about 6 trillion miles. And the nearest galaxy to the one we call home is 2.5 million of those stacked end to end. That's a gap so big the numbers almost lose their meaning. To drive it home, let's imagine you somehow had a spaceship capable of travelling at light speed, the fastest speed anything can theoretically achieve. If you launched today on a one-way trip to Andromeda, you'd arrive 2.5 million years from now. That's 10 times longer than humanity has even existed. And that's just for one galaxy, the closest one. Suddenly, the Milky Way feels smaller in your mind. It's enormous in its own way, sure, but it's just one member in something much bigger, a neighbourhood of galaxies. And this brings us to something known as the local group, which is exactly what it sounds like. A cosmic family of nearby galaxies bound together by gravity. The local group contains more than 80 galaxies, ranging from massive neighbours like the Milky Way and Andromeda to much smaller dwarf galaxies, tiny faint collections of stars that orbit the larger ones like moons around planets. It's a gravitational system, meaning these galaxies influence one another, interact and sometimes even merge. The entire structure spans about 10 million light-years across. Just take a moment to think about that. From end to end, the local group stretches 100 times farther than the width of the Milky Way, and yet it's considered a relatively tiny gathering of galaxies compared to the universe as a whole. Now, here's what's wild. Galaxies aren't just sitting frozen in place like some eternal cosmic wallpaper. They move, they interact, they evolve. Sometimes they collide and merge. And in fact, Andromeda and the Milky Way are on a direct collision course. That's right. In about 4 to 5 billion years, these two massive galaxies will slam into one another, twisting and distorting their structures and eventually forming something entirely new, a giant elliptical galaxy. But don't panic. Galaxies are mostly empty space, so when two collide, stars don't actually smash into each other like cars in a demolition derby. Instead, it's more like two mosquito nets passing through one another. All the stars and gas get rearranged by gravity, but the actual star-to-star collisions are rare. What's important here isn't just that galaxies collide, it's that even something as massive and seemingly eternal as a galaxy is still subject to motion and change. The universe is dynamic, always shifting, evolving into something new. Now you're probably thinking, okay, we've got these big galaxies like the Milky Way and Andromeda, but what about the smaller ones? Enter the dwarf galaxies. tiny galaxies compared to giants like the Milky Way, but still fascinating in their own right. Some dwarf galaxies like the Magellanic Clouds are actually visible from Earth's southern hemisphere. They're irregular in shape, loosely structured, and only a fraction of the size of larger galaxies. Where the Milky Way has hundreds of billions of stars, a dwarf galaxy might have just a few billion, or even just a few 100 million. That may seem like a lot, but on a galactic scale it's minuscule. But here's the thing, there are a lot of dwarf galaxies. In fact, they outnumber the bigger galaxies by far. They're like the small neighbourhoods surrounding massive metropolitan cities. These galaxies might not dominate the local group, but they still play an essential role in how gravity binds galaxies together into larger structures. And here's why all of this matters. The jump in scale from a single galaxy to an entire group of galaxies is one of the largest conceptual shifts in astronomy. When astronomers first realised that the Milky Way wasn't the whole universe, that there were other galaxies out there beyond it, it completely shattered centuries of assumptions about space and scale. Think about it. Every single star you've ever seen in the night sky belongs to the Milky Way. The universe we can visibly experience from Earth is a tiny fraction of just one galaxy. And yet all the stars, nebulae and systems you can imagine in our skies are nothing more than a speck in a much larger galactic ocean. But here's where things get really crazy. Even the local group isn't the end of the story. It's just one drop in an even larger ocean, a population of galaxies stretching across regions unimaginably vast, bound into even bigger structures called clusters, superclusters, and eventually into something astronomers call the cosmic web. Every time we zoom out, the true size of the universe refuses to stop growing. Every time we think we've reached an edge, we discover something bigger waiting beyond it. So while the Milky Way and Andromeda might feel vast, local group might feel even vaster, there are just entry points into the next step outward, an incomprehensible dance of galactic clusters filling the universe. Alright, let's take this journey one level higher. Up until now we've talked about galaxies, their stunning size, their structure, and how even a vast collection like the Milky Way fits into a small community of neighbours in the local group. But here's where the real mind-bending part begins. The local group itself, it's not isolated. It's part of something even larger. And once we step outside that cozy cluster of galaxies, the scales explode. This is where galaxies stop feeling like individual entities and instead become the building blocks of colossal structures that redefine everything we thought we understood about how matter is organized in the universe. Let's start with the concept of a galaxy cluster. If the local group is like a small town of galaxies, then a galaxy cluster is a sprawling metropolis. These clusters contain hundreds, sometimes thousands of galaxies all packed together and bound by gravity into a larger framework. Take the Virgo cluster, for example, the nearest large galaxy cluster to us, sitting about 54 million light-years away. This one cluster holds over 1,300 galaxies, and possibly up to 2,000, each filled with billions or even trillions of stars, countless planets, and who knows how many black holes. The sheer number of objects boggles the mind, and yet, in the grand hierarchy of cosmic structures, it's only a middleweight. Here's what's even more staggering. When you step into a galaxy cluster, the galaxies themselves stop being the dominant feature. That's right. The brightly glowing stars, the billions of points of light we think define the universe, are only a tiny piece of what makes up these clusters. Between the galaxies lies something darker, larger and harder to comprehend. First, there's the gas. Galaxy clusters are filled with vast amounts of superheated gas, so hot it emits X-rays, spanning millions of light-years. In fact, the mass of this gas far outweighs the combined mass of all the galaxies it surrounds. But even the gas, as massive as it is, doesn't tell the whole story. The real secret ingredient here is dark matter. Most of the mass in a galaxy cluster isn't even visible. It's dominated by an invisible form of matter that doesn't emit or absorb light but exerts an enormous gravitational pull. Dark matter is what allows these clusters to bind together and hold their shape. Without it, the visible galaxies and the gas would simply drift apart. So now we're faced with a jarring truth. Most of the universe is made of stuff we can't see or touch. We interact with the universe through light, but what actually builds these vast structures is largely hidden from us. But we're not stopping here. Clusters like the Virgo cluster don't just float alone in space, they are part of even larger formations called superclusters. If clusters are like cities packed full of stars and galaxies, then superclusters are the mega regions of space. They're enormous highways and junctions connecting clusters into even bigger systems. Our local group, along with the Virgo cluster, is part of a much larger cosmic neighbourhood called the Laniakea supercluster. Laniakea, whose name means immense heavens in Hawaiian, spans more than 500 million light-years. That's 500 million light-years across. At this scale, even galaxy clusters start to feel like specks of dust in a vast gravitational ocean. And here's the incredible part: superclusters aren't scattered randomly through the universe. They're part of a pattern that is even larger. For a long time, when astronomers began mapping galaxies and superclusters, they expected to find something like an evenly distributed arrangement. But that's not what they found. Instead, they discovered something so mind-blowingly vast that it challenges the limits of imagination itself. The universe, on its largest scales, forms a structure known as the cosmic web. The cosmic web is just what it sounds like: a network of interconnected strands and filaments stretching across the observable universe. These filaments are made of galaxies, clusters, and gas forming enormous tendrils that intersect at dense nodes where clusters and superclusters gather. Between these filaments are massive empty areas called voids. The entire universe, when viewed at this scale, stops looking like the random scattering of stars you see when you look up at the night sky. It starts to look like something alive, like a biological system with dense regions spread out across an unimaginable three-dimensional web. These strands can stretch for hundreds of millions, even billions of light years, making them some of the largest known structures in existence. But there's a paradox in the cosmic web that makes it all the more thrilling. While the filaments and nodes are packed with galaxies and matter, the vast majority of the universe by volume is made up of the voids. These voids are incomprehensibly large bubbles of emptiness, where the density of galaxies is far below the cosmic average. Some voids, like the Bootes void, are so massive they're over 330 million light-years across, with only a handful of galaxies scattered within them. These voids remind us that the universe's scale isn't just defined by how much there is, it's also defined by how much isn't there. Bigness in this sense is just as much about emptiness as it is about substance. So what does this all mean? It means that the universe isn't just big, it's architectured on a scale that breaks every intuitive sense of what structure should mean. At the level of the cosmic web, galaxies stop being individual units with their own sense of importance. They are like tiny droplets of water in a colossal network of rivers, streams, and oceans. Clusters, superclusters, and the cosmic web reveal a universe that is both full and empty, massive and sparse, shaped by gravity and by mysterious dark matter on cosmic timescales. And remember, these structures, the clusters, filaments, and voids that make up the cosmic web, are all part of just the observable universe. That's the part of space where light has had enough time to reach us since the Big Bang. What's outside of this web? What lies beyond the cosmic horizon? We have no idea. It could go on forever, or it could end in ways we can't yet comprehend. So let's pause for a second to process how much we've scaled up. We started with the solar system, then moved to the stars, then an entire galaxy, then a group of galaxies. Now we've reached clusters, superclusters, and the interconnected cosmic web itself. And even now, even at this scale, we haven't yet reached the limit of what we can imagine about the size of the universe. There's still one enormous question left to ask. How much more is out there beyond what we're able to see, Sam? And is there even an end to it? We're throwing around some enormous numbers here. 100,000 light-years across for the Milky Way, 2.5 million light-years to Andromeda, 500 million light-years for a supercluster. But here's the real question. How do we actually know this? It's not like scientists are out there with a cosmic measuring tape or hopping on a spaceship to clock the distances with a timer. So how exactly are astronomers measuring something as incomprehensibly vast as the universe with such precision? Here's the short answer. It's not a guess, and it's certainly not random. It's a step-by-step process built on centuries of science, connecting different techniques to bridge the gap between the near and the far, all the way to the edge of the observable universe. If the universe is impossibly big, the skill behind measuring it is no less impressive. To start with, cosmology depends on tools to measure distance, because without distance there's no way to talk meaningfully about the size of objects, the spacing between them, or their movement. Think about this. When you look up at the night sky, all those twinkling stars might seem like they're sitting together on a flat black canvas, but in reality, they're scattered across vast three-dimensional space at wildly different distances from Earth. Measuring those distances is the backbone of everything we know about the universe. Without accurate distances, any discussion about galaxies, expansion, or the cosmic web falls apart. So how does it work? Let's start small. The closest stars. The simplest and one of the oldest techniques astronomers use to measure distances is parallax. It's brilliant in its simplicity. As Earth orbits the Sun, the position of a nearby star appears to shift slightly against the far-off background of more distant stars. Imagine holding your finger in front of your face and moving your head from side to side. Your finger seems to jump compared to the objects behind it, right? That's parallax in action. For stars, the shift is insanely small, but it's there. Astronomers measure this minuscule change in position over the course of 6 months, as Earth moves from one side of its orbit to the other, using their baseline, the diameter of Earth's orbit, roughly 300 million kilometers, 186 million miles. From that data, they can calculate the actual distance to the star with simple geometry. But here's where your mind gets blown. Parallax only works for stars that are relatively close, within a few hundred light years. Beyond that, the shifts in position become so tiny that even the most powerful telescopes struggle to detect them. So while parallax is elegant and accurate, it only solves the first layer of the cosmic distance ladder. What about stars and galaxies that lie much farther away, beyond the reach of this method? That's where another key tool comes in: standard candles. A standard candle is any object in space whose brightness we already know. Once you know how bright something actually is, you can figure out how far away it is based on how bright it appears to be. Think of it this way. If you see a car's headlights in the distance, they appear dimmer the farther away they are. But if you know exactly how bright those headlights are up close, you can estimate how far away the car is based on how faint they look. Astronomers use certain stars and explosions as standard candles. One of the most important is a type of star called a Cepheid variable. These stars pulsate in a way that's directly tied to their intrinsic brightness. By observing them, astronomers can calculate their true luminosity and then measure their distance. Cepheids allowed astronomers to measure distances to other galaxies for the first time. And then there's the big one, Type 1a supernovae, which are powerful explosions of dying stars that always release about the same amount of energy. These cosmic events are like giant universal beacons that let us measure distances to galaxies millions, even billions, of light years away. Now, we've talked about measuring physical distance, but what about galaxies so far away that their light carries more information than just brightness? Enter redshift, the key to unlocking the scale of the universe. Here's how it works. Light from distant galaxies isn't just traveling through space, it's traveling through expanding space. Imagine a stretchy rubber band with marks on it. As you pull the rubber band wider, the marks move farther apart. Same deal with the space. As the universe expands, the wavelengths of light traveling through it physically stretch, shifting toward the red part of the spectrum. That's called redshift, and it's one of the most critical tools in modern astronomy. The farther away a galaxy is, the greater its redshift, because that light has spent more time traveling through an expanding universe. By measuring how much a galaxy's light is redshifted, astronomers can determine not only how far away it is, but also how fast space is expanding. This is why redshift isn't just about observing galaxies, it's about understanding the universe itself in motion. It reveals that the farther out we look, the deeper into the past we're seeing, because light from those distant objects started its journey billions of years ago. Finally, here's the thing about these measurements. None of them are perfect. Every method, from parallax to standard candles to redshift, comes with uncertainties. But science doesn't run on certainties. It runs on probabilities, refinement and comparison. When astronomers measure a distance, they don't say, "This galaxy is exactly X light years away." Instead, they'll say, "It's within this range, give or take." Over time, as our instruments improve and our methods become more sophisticated, those ranges shrink. We get closer and closer to the truth. But uncertainty doesn't mean ignorance. It doesn't mean we're guessing. It means we're working at the frontier of what's knowable. And this is one of the clearest examples of just how much we've learned. We're measuring the distance to galaxies billions of light years away, calibrating tools like a cosmic ladder, step by step, one method building on the next. Think about that for a second. Humans, a species that not so long ago couldn't even cross oceans, are now measuring the size of the universe itself. And we're not just throwing numbers out there. Every distance we quote, every light year we measure, comes backed by methods that link together like a chain from nearby stars all the way out to the edge of what light can show us. But here's the kicker. Even with all these advanced tools and steps, there's still one unavoidable truth. The size of the universe we're talking about here, the observable universe, is just the part we can measure. What lies beyond that edge? What happens when we hit limits we might never be able to cross? The question of size doesn't stop at our methods. It pushes us right to the edge of what can be known. Let's talk about light. You see it, you depend on it, and you probably take it for granted. But light isn't just something you flip on in a room or receive from the sun. Light is the ultimate storyteller in the cosmos. It's how we see stars, galaxies, and everything beyond. It's the carrier of all the information we have about the universe. And light has one key characteristic that changes everything about how we understand the size of the cosmos. It has a speed limit. In a vacuum, light travels at 299,792 kilometers per second, about 186,000 miles per second. That's fast enough to circle Earth over 7 times in a single second. It's the fastest thing in the universe, and as far as the laws of physics are concerned, nothing can outrun it, not even close. But here's the twist. It's fast, yes, unfathomably so by human standards, but it's not infinite. Even light takes time to cross space, and in a universe that's unimaginably vast, that delay becomes significant. In fact, it changes how you see everything. Because light takes time to travel, you never see anything as it is right now, you see it as it was. For example, think about the moon. It's about 384,400 kilometers away. So light from the moon takes roughly 1.3 seconds to reach Earth. When you look at the moon in the night sky, you're actually seeing it as it was 1.3 seconds ago, not truly in the present. The sun, on the other hand, is much farther, about 150 million kilometers away. That light takes just over 8 minutes to arrive, so even though we call it sunlight, what you feel on your face is light that left the sun more than 8 minutes ago. If, hypothetically, the sun were to vanish this instant, don't worry, it won't, we wouldn't even notice anything was wrong for 8 minutes. Now let's zoom out to stars and galaxies. The nearest star to the sun, Proxima Centauri, is over 4 light years away. That means the light we see from it began its journey 4 years ago. When you look at Proxima Centauri tonight, you're looking at a snapshot of it from 4 years in the past. For stars farther out, this delay grows exponentially. Sirius, one of the brightest stars in the night sky, is roughly 8.6 light years away. That means the scene you see when you stare at Sirius is almost a decade old. And this delay only gets more dramatic as we continue scaling up. At just 100 light years away, you're already seeing stars as they were before the Wright brothers invented the airplane. When we look at entire galaxies, the delays reach into millions or even billions of years. The Andromeda galaxy, for example, is 2.5 million light years away. So when we see Andromeda in the sky, we aren't seeing it as it is today. We're seeing it as it looked 2.5 million years ago, back when the first humans were just starting to emerge on Earth. Imagine that. The light from Andromeda has been travelling through intergalactic space for millions of years before hitting your eyes. And beyond Andromeda, there are galaxies whose light left its source billions of years ago, when Earth itself was still molten rock. What makes this so fascinating and kind of mind-bending is that astronomy isn't just about looking across distance, it's about looking into the past. The farther we look, the older the light we see. In a very real sense, telescopes are also time machines. Every time we study a distant galaxy, we're peering directly into cosmic history. For instance, when the James Webb Space Telescope observes galaxies 13 billion light years away, it's capturing light from a time when the universe itself was less than 1 billion years old. Think about that. The universe is currently 13.8 billion years old, and we're seeing snapshots of objects from its childhood, preserved in light that has travelled across space for almost the entire age of the universe. This makes the way we measure the universe radically different from, say, how we measure a physical object on Earth. On Earth, size and distance are static. You measure from point A to point B, and that's it. But in the universe, size and distance are tangled with time. Asking how big is the universe is also asking how far back into time can we see? Because as far as we can tell, the true scale of the cosmos is inseparable from its history. The deeper our telescopes peer into space, the deeper they peer into the timeline of reality itself. But there's a catch. While light can help us see into the distant past, it's not an open-ended tool. There's a limit to how much information light can carry. Here's why the universe has a finite age. It's about 13.8 billion years old. That means there's a fundamental limit to how far away we can see, because no light from farther than about 13.8 billion years ago would have had time to reach us. If something exists beyond that point, it's physically impossible for its light to ever get here. That's what defines the observable universe, the region of space from which light has had enough time to reach us since the beginning of cosmic expansion. Beyond it, the universe could extend indefinitely. We just can't know because no signal from those regions has ever, or will ever, reach us. But wait, it gets trickier. Because space itself is expanding, the objects we're seeing from 13 billion years ago are no longer 13 billion light years away. They've been swept farther by cosmic expansion. Today, those distant objects are about 46.5 billion light years away. So even though the light we're detecting from them comes from the distant past, their actual present-day distance is much greater than their light travel distance. This is why distance in the universe isn't static. It constantly grows, like dots on a balloon being stretched. And that means the observable universe is defined not by what you can physically reach, but by the limits of what light has brought to you. This naturally brings us to a question so big it almost feels philosophical. Beyond the light we can see, beyond the knowable regions of the cosmos, what lies out there? Is the universe infinite? Does it go on forever? Or does it have some kind of edge that's simply unobservable to us? The observable universe doesn't define the true size of the cosmos. It defines the limits of what we can know. And at those limits, science hits a wall. It's not ignorance. It's the simple fact that some information lies beyond causality, beyond light, beyond reach. Here's the thing. Size in cosmology isn't just about kilometers, light years, or even space. Size is also about time. It's about causality and the inherent limits of how far light, and therefore information, can travel. The universe isn't a static thing that you can stop, measure, and label. It's a dynamic, evolving system that we view through a lens of delayed light, one snapshot at a time. That's why every time we push the boundary of what we can see, we're also pushing into the limits of what can be known. And it's those limits, those barriers to knowledge, that bring us to the observable universe. How big is it not just in space but in time? And what secrets lie beyond the horizon we can never cross? Imagine this. The universe is 13.8 billion years old. So it's easy to think, the observable universe must be 13.8 billion light years in size. Sounds logical, right? But if that's what you think, prepare to have your mind blown, because that assumption, it's completely wrong. The observable universe is far larger than 13.8 billion light years. And here's where things get truly weird. The reason boils down to one thing: the universe is expanding. Space didn't just sit idle while light travelled. It stretched, pulling everything farther apart and making distances much greater than you'd intuitively expect. This is one of the hardest concepts to wrap your head around. But once you understand it, it changes how you think about everything we've been discussing so far. Here's the reality. The observable universe has a radius of about 46.5 billion light years. That's not a typo. It's 46.5 billion, not 13.8. Let's break this down. When we observe the most distant galaxies, what we're seeing is how they looked billions of years ago, shortly after the universe began. But in all that time, while their light travelled toward us, space itself has been expanding. Those galaxies, as we see them now, are much farther away than they were when the light we're observing first left them. Think about it this way. It's like watching a car drive away while standing on a moving conveyor belt that stretches underneath you both. By the time the car's headlights reach your eyes, it's much farther away than you'd think just from the light's travel time alone. That's what's happening on the grandest scale imaginable. So this brings us to a number many people struggle to even visualize. 46.5 billion light years to the edge of the observable universe in every direction, and that gives us a total diameter of 93 billion light years. That's 93 billion light years filled with hundreds of billions of galaxies, each holding billions or trillions of stars and who knows how many planets. This is the largest region we can currently define with confidence. When you ask how big the universe is, this is the best scientific answer we can give: 93 billion light years across, just for the observable part. But let's make something clear before moving on. This edge isn't an edge in the usual sense. There's no physical wall or boundary where the universe suddenly ends. The observable universe isn't like a big cosmic dome. The edge is just the farthest distance from which light has had time to reach us. It's defined by information, not by matter or structure. There could be more galaxies, stars, and cosmic structures beyond this horizon, maybe trillions of light years beyond. But if their light hasn't had time to get here, they're simply undetectable to us. The observable universe is a horizon of knowledge, not a limit of reality. And horizons, by their very nature, depend on your perspective. Someone in a galaxy billions of light years away would have their own observable universe, with its own unique view. This changes everything. The size and content of the universe aren't something you measure once and for all, they depend entirely on where you're standing. Now let's pull the scale back even further and talk about one of the most fascinating features of the observable universe: the cosmic microwave background. This is a faint glow of light detectable in every direction, and it marks the earliest time we can see. To understand it, we need to jump back in time to about 380,000 years after the Big Bang. Before this moment, the universe was a roiling, opaque soup of particles so dense and hot that light couldn't travel freely through it. The universe was essentially glowing plasma, and photons, the particles of light, were trapped, bouncing around like ping-pong balls in a foggy, crowded room. But as the universe expanded, it cooled, and finally, at this critical moment 380,000 years after the Big Bang, it crossed a temperature threshold where atoms could form, and that light could finally escape and travel freely through space for the first time. This ancient light, released when the universe became transparent, is still travelling today. We detect it as the cosmic microwave background, or CMB, a dim glow of microwaves across the sky and the oldest light that we can possibly observe. This is like the universe's baby picture, capturing what it looked like when it was only 380,000 years old. No telescope or future technology can see earlier than this moment, because light simply didn't exist as a travelling entity before this era of transparency. The CMB isn't just a boundary in space, it's a limit in time. Beyond it, we simply can't see directly, and this means that even the observable universe, enormous as it is, doesn't represent the full story. Billions, maybe trillions of galaxies could exist beyond this boundary. Space itself could be unimaginably larger than the region we can see. Maybe it even goes on forever. But for now, this region, the light-filled bubble with a radius of 46.5 billion light-years, is the largest swath of the universe that science can describe with direct observation. And yet there's this lingering tension we can't avoid. The observable universe is a real answer. It's the largest thing we can measure and study. But it's not the universe in its entirety. The true size of the universe could dwarf the observable portion by an amount that's impossible to imagine or express with even the best numbers we have. Here's the shocking part. Most of the universe, if not almost all of it, may forever remain beyond our ability to observe or even theorize about. The observable part is huge, yes, but it's also a tiny, knowable island in what might be an infinite sea of reality. So this brings us to one of the biggest questions of all. If the universe extends beyond our horizon, how much farther does it go? And is there any limit? Are we living in an infinite cosmos, or is there some kind of unknown edge lurking beyond the grasp of even the best science? To understand that, we have to look deeper into the very nature of space, possibility, and the mathematical structures that govern everything around us. But before we venture into infinity, we need to pause and reflect on this. The universe we can observe is already so vast, so ancient, and so complex that its boundaries might as well be edges of mystery itself. Let's address the question that's been building this entire time. Is the universe finite or infinite? How big really is everything? Here's the truth. It's one of the biggest questions in all of cosmology, and the answer is, we don't know. Not fully, not yet. We've built a framework for understanding the observable universe and its structure, its size, and even its age. But when it comes to the entire universe, the universe beyond what we can measure or maybe even imagine, it's still an open mystery. Let me be as clear as possible here. Science has made staggering progress in uncovering the cosmic story. We can confidently say the observable universe has a diameter of about 93 billion light-years. But when it comes to the total universe, the full extent of reality, there's no direct evidence that allows us to measure its size or determine its boundaries, if any exist at all. And this isn't because of a failure in science, but because of the nature of physical limits. The speed of light combined with the finite age of the universe creates a horizon, the observable limit. Beyond that, we simply have no information. Regions of space that are farther away than light has had time to travel are completely outside our observational reach. So what lies out there? More galaxies, endless voids, some kind of boundary? Or does the universe simply continue forever? Let's start with some modern clues. Observations of the universe's geometry give us some hints about its overall structure. Here's what we've found. On the largest scales, the universe appears to be flat. Now, don't get this wrong, flat doesn't mean two-dimensional. The large-scale curvature of space describes how it behaves rather than how it looks. Picture three possible shapes for space. If the universe were positively curved, like the surface of a sphere, travelling in one direction long enough would eventually bring you back to where you started. If it were negatively curved, like the surface of a saddle, space would hypothetically curve outward forever, creating a very different kind of infinite environment. But what the data suggests is that the universe is geometrically flat, meaning parallel lines stay parallel, and space doesn't curve dramatically at the largest observable distances. But here's the twist. A flat universe allows for two possibilities. It could be infinite, stretching on forever, or it could be finite but unbounded. This is where things get tricky. If the universe is finite but unbounded, it means that, much like the surface of Earth, it's closed in some higher dimensional way, so you would never reach an edge or wall of the universe even though it has a fixed size. Think of flying around the Earth. You could circle it endlessly without ever hitting a wall, because the surface just loops back on itself. But while this analogy helps, the universe isn't a two-dimensional surface, it's a three-dimensional space, and any higher dimensional closure isn't easy to visualize for, well, anyone. It's a concept that pushes human intuition to its limits. On the other hand, there's the other possibility, infinite space. An infinite universe means that reality doesn't stop no matter how far you travel. There's no loop, no boundary, no repeating tile, just an endless, limitless expanse of stars, galaxies, and matter, or possibly empty voids stretching in all directions. This idea is supported by models of inflation, the theory that shortly after the Big Bang the universe expanded at an exponential rate, stretching space far beyond what we can observe today. If inflation went on long enough, it could have created an infinite universe. But here's the catch. While an infinite universe is mathematically and theoretically possible, there's no direct evidence proving that infinity exists in reality. This is where cosmology lands in one of its most profound grey areas. A flat universe hints at an enormous scale, but it doesn't definitively answer whether the universe is ultimately infinite or just so vast that its curvature is undetectable within our observable range. Remember, the observable universe is only a fraction of the total universe, the part from which light has reached us. There's no reason to assume the universe stops at the cosmic horizon, but there's also no guarantee that it keeps going forever. And that absence of observational certainty is both tantalizing and strange, leaving the possibility open for models that diverge in dramatically different directions. It's also worth clarifying something important here. If the universe is finite, that doesn't mean it has an edge or a wall. Finite space can still loop or curve in ways that avoid boundaries. But also, if the universe is infinite, we need to accept something truly mind-bending. No measurement, no instrument, and no telescope will ever be able to capture the entirety of it. Infinity is not something you can measure, it's a concept, and an infinite universe would exceed both observation and physical computation. Here's one more thing to consider. Whether the universe is finite or infinite, what lies outside it? This is arguably one of the most puzzling questions of all time. If the universe ends, what's beyond it? And if it's infinite, how do we even comprehend that kind of endlessness? Modern science avoids the question of outside by framing the universe as everything there is, the complete totality of space, time, and matter. In theory, there's no outside of everything, there's just more universe, whether it curls back on itself or continues infinitely. So where does this leave us? At a stunning crossroads. The observable universe gives us a vast but measurable bubble of knowledge, and beyond it lies a question mark the size of, well, everything. Humanity has measured incredible distances, traced cosmic history, and brought light to some of the deepest mysteries of existence. But even after all that, the full extent of the universe remains elusive. It could be a finite reality so vast we'll never uncover its boundaries, or it could stretch endlessly, defying measurement and the limits of our imagination. But here's the part that really matters. The fact that we don't yet know isn't a failure. It's part of the story. The universe isn't simply big. It's bigger than our instruments, bigger than our ideas, bigger than the concepts we use to try and define it. And maybe, just maybe, that's what makes it so incredible. The final word on the universe's size may be forever out of reach, but the search itself tells us something profound. In a cosmos so immense, the act of asking the question might be just as important as the answer. Let's start with a simple fact that sounds impossible. The universe is getting bigger. And it's not just that things inside the universe are moving apart, it's that space itself is expanding. This is one of the most counterintuitive but foundational concepts in all of cosmology, and it changes what we mean when we talk about the size of the universe. The universe is not a giant static container with galaxies bouncing around inside it. It is an ever-growing dynamic system where the actual fabric of space is stretching, pulling the galaxies farther and farther apart. But here's something important. Not everything in the universe is expanding. The solar system isn't stretching, Earth isn't inflating like a balloon, and you don't wake up each morning slightly taller because of cosmic expansion, thankfully. The reason is that at small scales, inside galaxies, solar systems and other structures, gravity, electromagnetism and other forces hold everything together too tightly for the expansion of space to affect them. But on the largest scales of reality, where the forces of nature are stretched thin, space does expand. And that's where things get wild. This realization that the universe's size is not fixed completely shook the scientific community when it was first discovered. For most of recorded history, people assumed the universe was static, eternal, and unchanging. Sure, stars might move around, but the overall cosmos itself? That was thought to be fixed. Then came one of the most transformative moments in human understanding of the cosmos, thanks to a man named Edwin Hubble. Back in the late 1920s, Hubble looked at distant galaxies and not only noticed that they were moving, but that they were moving away from us. More than that, he found that the farther away a galaxy was, the faster it was receding. This wasn't because we were in some weird cosmic explosion or because those galaxies were fleeing from us specifically. It was because space itself was stretching in every direction. The universe wasn't static, it was expanding. This discovery shattered the old world view. It meant the universe had a history, a beginning. If the expansion has been happening for billions of years, it also means that earlier in time everything was much, much closer together. The modern concept of the expanding universe was born, and with it came entirely new questions about the nature of the cosmos itself. One of the biggest implications of this expansion, and it's something we mentioned briefly earlier, is that it explains why the observable universe isn't just 13.8 billion light-years across. Remember, the universe is about 13.8 billion years old, and light travels at a finite speed, 299,792 kilometers per second, or about 186,000 miles per second. Simple math might lead you to think the observable universe would be 13.8 billion light-years in radius, because that's how far light could have travelled since the beginning of time. But here's the catch. Space has been expanding while that light was on its way to us. The galaxies emitting that light billions of years ago are now about 46.5 billion light-years away. Every second of a photon's journey is spent in a universe that's stretching wider. By the time that photon finally arrives, the distance to its origin is far greater than its travel time suggests. Expansion rewrites our common sense understanding of both distance and time, forcing us to think about the universe as not just vast but actively evolving. But here's where things get even stranger. The universe isn't just expanding, it's expanding faster over time. How do we know this? Well, in the late 1990s, astronomers studying distant supernovae, those brilliant explosions of dying stars, made a shocking discovery. They found that the expansion of the universe wasn't slowing down as they'd expected. Instead, it was accelerating. Picture that conveyor belt analogy again, except now it's speeding up the farther you are from its centre and the longer time passes. The galaxies at far distances aren't just moving away, they're moving away faster and faster. This acceleration in the expansion is being driven by something mysterious that scientists call dark energy. Dark energy isn't something we can see or directly detect. It's not like dark matter, which interacts through gravity. Dark energy is different. It's a kind of invisible force, or maybe something even stranger, that seems to be woven into the very fabric of space itself, causing the universe to expand at an ever-increasing rate. Here's the truly unsettling implication. If this acceleration continues indefinitely, the farthest galaxies we can see today will one day slip beyond reach. The accelerating expansion will stretch space so much that their light will never be able to reach us again, no matter how powerful our telescopes become. In the unimaginably distant future, entire galaxies may disappear from view, leaving the universe feeling secure and lonelier than ever. And this isn't just theoretical, it's already happening. Some galaxies are already moving away so quickly because of cosmic expansion that their light will never reach Earth, no matter how much time passes. In a universe defined by acceleration, the concept of distance gets tangled up in destiny. Things that are far enough away will be permanently locked outside our observational reach. What we see now is only a temporary snapshot of what's possible to perceive. The universe's size, in a sense, isn't just a question of where things are, it's also a question of when we're asking about them. This brings us to a fundamental realization. The bigness of the universe isn't static, it's dynamic. In our ordinary lives, large things tend to stay large. Mountains don't grow overnight, and oceans don't expand because of time. But in cosmology, size itself is a moving target. The universe started as a hot, dense, tiny point, expanded rapidly during the period of cosmic inflation, continued growing under the influence of gravity and dark energy, and is still spreading out today. Even if we could freeze time and measure the universe's size right now, it wouldn't stay the same for long. Expansion ensures that the universe's scale is always tied to its history and its future. So when you ask how big is the universe, there's always an unspoken follow-up. Do you mean how big now, how big in the past, or how big will it become in the distant future? The size of the universe is not a single static fact. It's a story. A story written across the largest stage that has ever existed. A story of which we've only begun to glimpse the first few chapters. Let's talk about numbers, specifically big numbers. Numbers so huge they break your sense of reality. And here's the thing, your brain is not built to deal with them. When you hear that the observable universe is 93 billion light-years across, or that it contains around 200 billion galaxies, each with billions or trillions of stars, it's easy to say, wow, that's big. But do you really grasp what those numbers mean? Probably not, and that's not your fault. It's how human intuition works. Let's start small, or at least what feels small compared to the universe. Imagine a billion. Not a million, but a billion. A million seconds ago, that's about 11.5 days. A billion seconds ago, that's over 31 years. The difference between a million and a billion isn't just a little more. It's 3 orders of magnitude bigger. And yet when people hear the word billion, it tends to blur into a lot. It's just too big to visualize. But in the universe, billions are everywhere. The Sun is one star out of around 100 to 400 billion stars in the Milky Way. The Milky Way is one galaxy out of roughly 200 billion galaxies in the observable universe, though that estimate keeps rising as our technology improves. Now start stacking those billions. Billions of stars multiplied by billions of galaxies. You're looking at a total star count somewhere in the range of 1 sextillion stars. That's a 1 with 21 zeros after it. And even that doesn't include the unknown expanse beyond the observable universe. Let's pause for a second. If wrapping your head around billions is already hard, what do you think happens when the numbers go exponential? This is why analogies come into play. A typical analogy might say, if each star in the observable universe were a grain of sand, you'd have enough sand to fill a planet-sized beach. Seems helpful, right? Except it's not the full picture. Analogies like these are tools. They help shape a mental image, but they can also distort reality. For example, if you think of galaxies as islands and stars as cities, you might imagine the universe as packed full of islands and cities, busy, overflowing, crowded. But the actual universe is nothing like that. The analogy fails because what really dominates the cosmos, what makes the universe so breathtakingly large, isn't the stars or the galaxies or the so-called islands, it's the space itself. Empty space is the true king of the universe. Let me put it like this. Within our solar system, Earth feels enormous. It takes hours of flight just to cross a country, days on a ship to cross an ocean. But when you zoom out to the solar system, Earth becomes an afterthought. The planets are tiny beads scattered across tens of millions of kilometers of empty space. Now step out to the interstellar scale. The Sun, massive compared to Earth, shrinks into insignificance when you think of the 4 light-year void separating it from Proxima Centauri, its nearest stellar neighbour. And when you expand to the galactic scale, the hundreds of billions of stars in the Milky Way, massive as they are, still float inside a galaxy that's mostly empty. The Sun is 1.4 million kilometres in diameter, but it orbits 26,000 light-years from the centre of the Milky Way. Think about that ratio. Massive objects, separated by unfathomable emptiness. The same happens at the larger-than-galaxy scale. A galaxy might contain hundreds of billions of stars, but the distance between galaxies is even more absurd. For instance, the Andromeda Galaxy and the Milky Way are separated by 2.5 million light-years of space, and that's considered close by cosmic standards. The observable universe itself, mapped at its largest scales, forms a vast web of filaments and clusters where galaxies group together. But guess what's in between those clusters? Enormous voids. These are dark regions millions of light-years across, sparsely populated by galaxies and containing almost nothing except thin gases and maybe a little dark matter. The universe feels gigantic, not just because there's a lot of stuff in it, but because most of it is empty. So here's the big takeaway. Scale in the universe isn't static. It redefines itself every time you climb one level higher. At the planetary level, Earth is big compared to the Moon. But at the stellar level, Earth becomes insignificant compared to the Sun. At the galactic level, even the Sun becomes one insignificant spark lost in a sea of other stars. And at the cosmic scale, the Milky Way itself, this massive city of hundreds of billions of stars, is just one dot in a vast cluster of galaxies. By the time you step back far enough to see the observable universe as a whole, even the biggest galaxies become tiny, like grains of sand spread across an inconceivably large cosmic web. Every time you think you've got a handle on scale, the universe pulls the rug out from under you and says, try again. This escalation is one of the reasons why truly comprehending the universe's size is almost impossible. But here's the thing, that's okay. The universe isn't designed to fit neatly into our heads. In fact, you wouldn't expect it to. Our brains evolved for survival on a single planet, where the largest things we interact with are mountains and oceans. The fact that we're even able to calculate the size of the observable universe, that we've pushed our understanding as far as we have, is already astonishing. And maybe it's not about holding all of it in your head at once. Maybe the beauty of it lies in the tension. Our limitations as humans confronted by a cosmos so vast, so ancient, so full of distances and numbers, that it escapes not just measurement but imagination itself. That's the magic of trying to understand the universe. Not that you'll ever completely get there, but that you've even started. So after all this, here it is, the most straightforward, concrete answer to how big the universe is. The observable universe is about 93 billion light-years across. That's it. That's the cleanest number we have. It's not just a guess. It's a result of rigorous science, built from decades of measurements, observations, and calculations. It represents the largest region we can currently understand and study. A bubble of accessible space roughly 46.5 billion light-years in radius around Earth, spanning not just galaxies and stars, but all the light, matter, and energy whose signals have had time to reach us since the beginning of cosmic expansion. And this number, it's vital to grasp. It includes everything physically reachable with light emitted since the Big Bang. It accounts for the expansion of space. It's not 13.8 billion light-years because, as we've discussed, the universe isn't static. Light has been travelling through an ever-expanding fabric of space-time. So when those photons arrive, their origin points have stretched to 46.5 billion light-years away. That's where we get the 93 billion light-year diameter. And as enormous as it is, 93 billion light-years of galaxies, structures, webs of matter, it's still not the whole story. It can't be. Because the real answer is, we do not know how big the universe truly is. And this realization blows everything open again. What's out there beyond that 93 billion light years? In truth, beyond the observable universe is a vast, unreachable sea of possibilities. Maybe that first boundary we're so confident about is just a tiny dot on a much larger stage. Or maybe, brace yourself, we live in an infinite cosmos, a universe of endless galaxies and stars that stretch on eternally beyond every horizon, defying not only observation, but even concepts like completion or edges. Let's pause here for a second, because this is where things get both exciting and unsettling. Science, with all its brilliance, is in some sense bound to observation. We can measure what we can see and we can infer what we can model, but when it comes to asking about everything beyond observation, we're left with uncertainty. And that uncertainty does something profound. It transforms the universe from just being big into being an open-ended mystery. We've measured the observable part, yes, but the actual total universe. It could be finite but unimaginably larger than what we see, or it might truly have no boundaries, no edges, no end, just infinite space-time that keeps going in all directions forever. This uncertainty isn't just about size, it's about how the universe is large. The cosmos isn't just large in terms of physical space, it's large temporally. Because every light signal we receive brings pieces of history with it, billions of years worth of it. Imagine seeing something 10 billion light years away. You're looking at an event that happened 10 billion years ago. The size of the universe is inseparably tied to its timeline, stretched across epochs that feel impossible to fathom for creatures who live decades, not eons, and it's large structurally, because the universe doesn't just exist as empty space. It forms webs of galaxies, vast assemblies of clusters, layered systems that repeat and build on every scale, from planets to filaments, arranged in patterns more intricate than any natural mind can intuitively understand. The size of the universe is everything at once: space, time, history, architecture. It's all of these concepts crashing into one another at scales that redefine the limits of thought. Now here's something even more extraordinary. As vast as the observable universe is, the biggest shock might not be its size, it's our position within it. Have you noticed just how unimportant Earth has become as we've zoomed out step by step? To us, Earth is everything. It's the rock where life began, the home of mountains, civilizations, and oceans. But the moment you leave the solar system, it shrinks to a blip. By the time you're orbiting near Proxima Centauri, it's gone, no more visible than the dust on your desk. When you zoom all the way up to the scale of the Milky Way, the Sun, our magnificent life-giving star, is itself just one ordinary dot in a city of more than 100 billion other stars. And as we climb outward, the Milky Way itself becomes just one galaxy among 200 billion more, part of the local group, a region so small on the cluster scale that it's practically nothing. Philosophically, this could be crushing, but it doesn't have to be, because take a moment to appreciate what's really happened here. We don't occupy some special central place in the universe. Earth is not cosmically privileged. It is one tiny piece of an incomprehensibly large puzzle. And yet, somehow, here we are, on this little planet, able to study and ask these enormous questions. From a random spot in one galaxy among hundreds of billions, our species has mapped cosmic background radiation, catalogued galaxies, calculated the age of the universe, and measured how fast space itself is expanding. That's stunning. We might be small, but we've reached for knowledge on scales that speak to the very heart of what it means to be human. And now, we're back to the big question. How big is the universe, really? Well, the answer isn't just huge. That's not enough. The universe is so immensely vast that the part we can observe already breaks language and imagination. But the real kicker, this observable section might be nothing more than a local chapter, a single page in a book that keeps going and going farther than we'll ever be able to read. Here's the most honest answer we have. The observable universe is about 93 billion light-years across, and it contains billions upon billions of galaxies, each filled with stars and planets beyond counting. But the total universe, that answer is still in the making. Maybe it's finite, with edges that stretch far beyond what we'll ever detect. Or maybe it's infinite, a cosmos that defies even the concept of boundaries. What we know is that the universe is so big that it will outlive anything we build, outlast every map we create, and exceed every horizon we think we've reached. And this is what makes the universe not just big, but extraordinary. It's big enough to dwarf imagination. It's structured enough to be studied, piece by piece. And it's mysterious enough that the ultimate boundary, if there even is one, has not yet been found. What lies beyond what we know? That's where you, the question asker, enter the picture. Because the size of the universe is big, yes, but what's bigger is the wonder it inspires. Thank you for travelling through the cosmos with me. The journey of asking how big the universe is doesn't have a final stop. It's endless, just like the universe itself may be. And that's exactly why the question matters so much. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.